Okay, so I'm going to import this data into SPSS. And we're going to ask SPSS to calculate the 95% confidence interval for those numbers, those number of slices. I'm going to say open data, and I'm going to navigate to where my data is located, which is on my desktop, and they make me go through, for an expensive program, they're not really convenient. Now I got this, and now I can't do it by dates. I got to find which one it is. I think it's that one. There we go. Corned beef. There you go. I could have imported it from the Excel file, but I already had it that way. Okay. So if you, just to show you, I can import it from the Excel file. Open data. I go to the same place. I don't see the Excel file here in that folder with all my files because it's only looking for .sav files, SPSS files. If I go down here and tell it, look for Excel files, well, now see it finds that corned beef file. And if I say open, it comes up and it asks me a couple of quick questions. It says, oh, I see data between A1 and A17. That's because the first one says slices, right? It's a variable name. Okay, there's a little checkbox here. Read variable names from the first row of data. I leave that checked off because the first row of data was not actually data. It was the variable name. So I say, okay, and it imports it, and I have that data file in here again. So now I'm going to go up to Analyze, Descriptive Statistics. I'm going to go all the way down to Explore because I could go into descriptive statistics, descriptives, but Explore gives me more information. Explore. I only have one variable, slices. So I'm going to move that into my dependence list. I'm going to click statistics just to make sure it's got calculate the descriptive statistics and calculate the confidence interval for the mean 95% confidence interval. I'm going to say continue, and I'm going to say OK. Okay, and SPSS cranks and grinds, and it comes up with the answer here. And the mean was 10.06, same as we calculated ourselves. The standard deviation was 3.13, same as we calculated. And the 95% confidence interval, is it here? Yeah, there it is. It's 8.39 to 11.73. It always does. Even if the sample size were 100, it would go to the t-table, and instead of using 1.96, it might use 1.97. It always uses the t-table because it can. Why not? It's a computer. It could look it up as quickly as it could just assume 1.96. After we get to 30, we use that 1.96 as a convenience, right? But if we don't know the population standard deviation, we're always guessing at a little bit more by using the sample standard deviation, and the t-score makes up for that. Okay, so now if you're using a population proportion, what's the difference? How would that change what you're doing with the population proportion? It doesn't, right? Because with the population proportion, we always use the z-table. Why? Because we're always, one of the assumptions is you got to have a sample size greater than 30. So 15 and 15 in each group. So we don't care about the t-score when we're using sample distribution. Okay, so now let's try another. How much time we got? Let's try another couple of examples. Let's for the hell of it just do a population. Let's do a proportion. Okay, suppose we want to know the true population proportion of Irish Americans who approve of a wider representation of all groups of St. Patrick's Day Parade. 2000 Parade Committee has a random sample, so on and so forth. This is all nonsense. This is all made up. Out of 1,381 respondents, big sample, 496 said that they approved. What can we say about P, the population proportion? Now, we know that 496 out of 1,381 said that they approved. Okay, so now what is the p-value? What is the p-value? We don't know the p-value. P-value, we usually use that term p to represent that. We use it to represent the population proportion. We don't know that. We didn't sample the entire population of Irish people in New York. Okay, so what we know is p cap. Okay, and p cap is equal to, what is p cap equal to?
Is it 496 over 1,000?
Exactly right. Okay, and it meets our minimum criteria for sample size. Each group, one group is 496. The other group, people that didn't approve, were 496 subtracted from 1381. So both of those are more than 15, way more than 15. Okay, and so P cap is equal to, let's get this,
0.353.
496 divided by 1381, okay, is 0.359. What's that? Type them on? Yeah, I just can't. I can't do it because I don't know. They confuse me. I need a numeric keypad, I guess, or something. Okay, it's 0.359. It is frustrating, right, to watch me do that. It's twice as frustrating for me. Okay, so at any rate, 0.359. So that's why I keep yelling at you guys to do the calculation for me, so I don't have to do it. But nobody pulls out the calculator. So at any rate, 0.359. So now I don't know. Well, I know my sample has a proportion of 0.359. But what I'm really interested in is what proportion of people in the population of Irish people that are going to attend the parade approve. And I can never know that. But now that I've taken this sample, I can at least calculate a confident, 95% confidence interval for what the true proportion is. In other words, maybe I'll get lucky and maybe it could be 50% or more. Maybe this sample is a little underestimated. So let's see if there's a 95% chance that maybe it could include 50%. Maybe there wouldn't be a majority against. Okay, so how am I going to calculate that? It's going to be equal to P cap plus or minus, and it's going to be 1.96 because we're always going to use the z-score times the standard error. Okay, so let's calculate our standard error. Standard error is going to be equal to the square root of 0.35, 0.36. I'm going to round this off. 0.36 times 0.64 divided by, all of that divided by, I'll put this in parentheses, divided by the sample size, which was 1381. Right? And this is going to be the square root of this entire thing. Maybe I can get lucky and actually copy and paste this into Excel. Let's give that a try. Did I make a mistake there? Oh, you're telling me the answer. Oh, excellent. Thank you very much. Hang on a second. Let me. Maybe I'm just want to see if I can't actually copy this into Excel. Equals square root of. Let's see if we get lucky here. Oh no, it worked out. Did I get it right? Yep. 0.012. I think you were off just a little bit. You may not have rounded off. Remember, I rounded. And remember, I keep telling you, don't round off until you're done because you took square root, and so it's automatically more than the amount of error that you rounded by. Okay, so my P cap is going to be equal to 0.36 plus 1.96 times this number, my standard error, and it's going to be equal to 0.36 minus 1.96 times my standard error. Whoops, mess something up there. Times, I see. I didn't multiply, I added. Times. There we go. So my true proportion of people that approve is between 33 and 39%. So what does that tell you? That tells me that I'm 95% certain that a majority of people don't approve of the people that are attending the parade approve, because 50% is outside of my 95% confidence interval. So that means something to me. That means that I'm 95% sure I would, if I put it to a vote of everybody, that I wouldn't have a majority that would approve. Okay. What does that mean? That means we have a tool for prediction. Okay. And now we're going to do another problem that's going to use that tool for prediction. We're going to do it in a form that's called hypothesis testing. Okay. So, I'm going to get rid of this. So now I'm going to open this. Yes. Okay. A fellow student says that the average salary graduates in your major is $40,000 per year. You don't think that's correct. You think the average salary is higher. And to show, I'm going to say different. I'm not going to say higher. There's a reason why I'm saying different, not higher, because that's a one-sided test. We're almost 90% of the time, 95% of the time, we're going to be doing two-sided tests. Shows it's wrong. You take a simple random sample of 100 graduates who have graduated in the past 5 years and ask the amount of their salary. You find that the sample mean is 31,000. Its sample deviation is, I'm going to change that number a little bit. I'm going to call it 35,000. And the sample standard deviation is 4,000. Is there evidence to support your claim that the population mean standard salary is greater than 30,000? Okay, so what are our assumptions here? First of all, what's our assumption on our sampling? That we took a random sample and that all of the people in our sample are independent, right? They're not all from the same major, right? We randomly sample people from all different majors and so on and so forth. They're independent samples and they were obtained randomly, okay? Random and independent. Okay, so what's our null hypothesis here? Well, what did we say about the average salary, right? The average salary is equal to, no, that's what our sample says. What did we say about, what's our null hypothesis? Our null hypothesis is that the average salary is 40,000, right? What's our alternative hypothesis? Alternative hypothesis is that mu is not equal to 40,000, right? All you're trying to do is prove that he's wrong, that it's not really 40,000, right? He says the average salary is 40,000. You think you don't think this is correct. So the null hypothesis is that the average salary is 40,000. Your alternative hypothesis is that it's not equal to 40,000. Could be less, could be more. As it happens, you're going to test that. Actually, you wouldn't know any of this stuff before you made the argument, right? You made the argument. It's going, now I'm going to go out and prove it. I'm going to take a sample. I'm going to sample 100 people randomly, 100 undergraduates randomly, and find out what their salary is. Turns out that your sample mean is 35,000. That doesn't mean that he's wrong. Your sample could be, by chance, less than, the population could still be 40,000, but your sample mean could be off. Could be different than the actual population mean. Now you have to figure out whether or not your sample mean is different enough for you to say with 95% certainty that he's wrong, or with 5% chance of being wrong, less than 5% chance of being wrong. Okay, so since it's a large sample, we can actually kind of look at our z-score to kind of give us an idea of whether or not this is true. Okay, so let's take a look at what mu is. So I'm going to take a look at mu, and I'm going to subtract x bar. I want to see how different they are, how many standard deviations apart these two values are. So mu minus x bar, and how many standard deviations apart are there? Well, for a sample this size, mu minus x bar divided by the standard error. That's how many standard deviations apart they are. Okay, that's going to be my z-score, or number of standard deviations apart. Okay, had I been working with a sample size less than 100, or less than 30, I would have called that t is equal to the difference. Number of t-scores apart that they are is the difference between those two. So what is that equal to? That's equal to mu, let's see, that's equal to 5,000, right? One's 40,000, the mean is, he predicted was, the null hypothesis says mean is 40,000. The alternative hypothesis says that our mean that we calculate is 35,000. So it's 5,000 divided by the standard error. Now, what's the standard error? Well, the standard deviation was 4,000, but it's a sample size of 100. The difference between 40,000 and the sample mean. Okay, in other words, okay, I'll do this. I'll add an extra line here. Z, Yes. Is equal to?
That one is 31,000.
I'm sorry, I changed it. I changed it on mine. I made them closer together. Because I think it's going to come out nasty if I don't make them closer together.
So it's supposed to be 35.
Yeah, I changed it to 35 on the fly. Okay, so it's 40,000 minus 35,000, right? Divided by my standard error. What's my standard error going to be? It's going to be my standard deviation, 4,000, divided by the square root of the sample size. Sample size is 100, so divided by 10. So my standard error is going to be 10. It's going to be 400. Excuse me. My standard error is 4,000 divided by 10. Okay, I'm going to change that number again. They're too far apart. I'm going to change that to 39,000. Okay, so now this is 40,000 minus. I'm going to take our sample result and change the average to 39,000. So Z is going to be equal to the mean from the null hypothesis, our original mean that we're saying on null hypothesis is minus X bar, which is 39,000, divided by the standard error, which is 4,000 divided by the square root of 100, which is 400. So what is Z equal to? Z is equal to 1,000 over 400, which is equal to 2.5. Okay? So if I looked up yes.
So when you took a z-score, you said mu minus x bar, but I thought the formula was x minus mu.
It doesn't matter. Okay, well, let's see what happens if I use x minus mu. X bar minus mu. Minus mu. Minus mu.
So you just get a negative.
Yeah, you get same result. It's going to be negative. And what do we know about the normal distribution? It's symmetrical, so it doesn't matter if you got a negative 2.5 or a positive 2.5. Okay, so this time it comes out to a negative 2.5. If I go to my Z table now, what's the probability of getting a result where these two are 2.5 standard deviations apart? I'm going to go to my Z table. Okay, and I think I got it on here. Where's my Z table? Here's my Z table. I think I got it open already, so that's why it's not popping up. Oh, that's my T table. Got all excited there. I had it. That's my T table still. This is my Z table. There we go. So negative 2.5, negative 2.50. The left tail is 0.006%. That's less than 6%, right? So I have a left tail that's 0.6%, right? Now remember I said it could have been either way. I could have gotten the result that was bigger than the true mean. So I have to consider that I've got 0.6% over here is the probability of getting with this sample size, the probability of my getting a result for a mean of 100, a sample size of 100, probability of getting a mean that's that extreme is less than 1%. It's 0.6%, right? Now I have to consider both sides. So I actually have to, not only look at the left tail, I have to look at the right tail. So really, the probability is 0.6 for the lower tail and 0.6 for the upper tail. So the probability of my getting a z-score, a difference in number standard errors apart for the predicted mean and what my sample size says, the probability of getting them that far apart is only 1.2%. Okay? Now, how confident do I want to be to say that there's a difference between the two of these? What number comes to mind mostly? 95%. Being 95% confident is kind of the same thing as finding a 5% chance of being wrong acceptable, right? So we want less than a 5% chance of being wrong. We're going to call that chance of being wrong alpha. So along with a 95% confidence interval, we're going to use another measure of error and talk about alpha error, okay, or type 1 error. We want, before we reject the null hypothesis and say that guy's wrong, the average salary is not 40,000, right? It's something different than 40,000. In this case, it looks like it's lower, but we didn't really care. We just said different, right? So in order for me to reject my null hypothesis, remember what my null hypothesis was? That the mean is equal to 40,000. In order for me to reject that, I have to have an outcome for the sample mean that has less than a 5% chance of occurring if the sample mean, if the population was really salary was really 40,000, right? What percentage was the chance of being wrong? What percentage of getting that outcome? It was only 1.2%. That's called my p-value, my probability of being wrong if I reject the null hypothesis. I want my p-value, probability of being wrong if I reject the null hypothesis, I want that to be less than 5%. So alpha needs to be less than, p needs to be less than alpha. Alpha is 0.05, p needs to be less than 0.05. So p is less than 0.05. So I reject my null hypothesis and I accept my alternative hypothesis that the average salary is different than 40,000. Now, what if the mean salary in my sample was 39,500? Well, my z-score would have only been, let's see, you got 500 difference and the standard error was 400. My z-score would have only been 1.25. Right? Would I have gotten an area here that was less than 5% or less than 2.5% on each side if my z-score was only 1.25? No, I wouldn't. So my p-value, in other words, if my z-score came out to be 1.25, that'd be roughly 7% on the bottom and 7% on the top, 14% chance of getting that big a difference when I did my sample with the predicted mean. Right? 14% chance of getting a z-score difference between number of standard errors difference between my predicted mu and my sample mean. It's a 14% chance of being wrong. What's my acceptable level of error? 5%. So I fail to reject the null hypothesis. Okay. Getting confusing, right? Yeah, okay. That's good. That's good. It's supposed to get a little confusing. Yes.
We've done the z-score enough for that to be obvious.
Yeah.
We used the z-score and we got 1.06.
Yes.
Which is then times 2 is 1.2.
Right.
That's your p-value.
That's my p-value. That's the probability that I would get that big a difference between those two numbers.
What big is it?
That big number of standard errors between mu
Sample mean
and mu.
and mu.
Exactly. Yes.
That big a difference meaning that it could.
In other words, this guy's predicting, we're testing whether or not the sample mean is 40,000, right? I take my sample, right? My sample could be 39,500. It could be 36,000. The chances that you would get that big a difference, 36,000, is very small if the population mean was really 40,000. The further apart those numbers are, the less likely that mu is really 40,000 when you take your sample. Remember, we don't really know what mu is. We're only predicting. Somebody told us that we think it's 40,000, and we're trying to disprove that. Okay? So if we take a sample of 100 people and it comes out 39,000, well, that's a big enough difference for us to say with more than 95% certainty, less than 5% chance of being wrong, that it's not 40,000. It's got to be something different than 40,000. But if the mean had come up 39,500, I wouldn't have a big enough difference to say that. And why don't I have a big enough difference? Because what I'm focusing on is the number of not the actual values, but the number of standard errors those two are apart. Okay? If you're two standard errors apart, right, then you're 95% sure that they're different. If you're 1.5 standard errors apart, you're not 95% sure, because they're not far enough apart for you to say they're really different with that level of certainty. Yes?
Tony, quickly again, to get the proof point. With the P and the alpha relationship, could you just briefly explain that criteria to reject and accept again?
Okay. If your z-score, when we calculate it here, is greater than 1.96, whether it's a negative number or a positive number, if your z-score, the number of standard errors apart, is greater than, say, 2, 1.96 actually, but 2, right? Okay. If they're that far apart, you can say with 95% certainty, in other words, 5%, less than 5% chance of being wrong, that your null hypothesis is not true, that the population you took the sample from is not the same as the predicted population mean, right? They're not the same because there's 2 standard deviations apart, those numbers, or more than 2 standard deviations. If they're not more than 2 standard deviations apart, they're not far enough apart for you to say with 95% certainty that they're different. Okay, so now let's think about this. If I have a sample size of 25, right? Can I use 1.96 as the distance that I need apart? What do I have to use instead? The t-score. So if I have a sample size of 16, in order for me to reject the null hypothesis, how many standard errors apart do they have to be? They have to be at least 2.131. Remember, that's what we looked up. Then you can reject the null hypothesis. Kind of neat, right? This is really kind of what we're doing. What we're doing right now is called a single sample t-test. This is your first look at hypothesis testing. So, I wouldn't go too nuts on this yet because we're going to do a lot of this stuff. Maybe some of it might be, right? We'll have to discuss that. Well, you get some practice on it. There's a bunch more practice problems and stuff like that. And we don't have time to go through them now, but we can do them online. And I'll set up like a review session, like Saturday or Sunday or something like that. Yeah. Okay, good. I'll tell you what. There's another sheet of examples here, right? That's 7C. I'll make sure that you have the answers for them. Okay, and then we'll go over them too. Yes.
So, you said if the z-score is greater than
1.96 standard deviation, you can reject the null hypothesis.
so it's meaning that they're different.
Yes.
So what was the point of even doing the percentage for the 1.2% difference?
I'm sorry. Oh, no. Yeah, you're right. All you needed to know is that there were 9. You're exactly right. You are exactly. That's very insightful. You're exactly right. All we needed to prove with 95% certainty, less than 5% chance of being wrong, is that there are 2 standard deviations apart, 2 standard errors apart, right? But by calculating it, not only do you know that your chance of being wrong is less than 5%, but now you know what your exact chance of being wrong is. Now you know your chance of being wrong is not just less than 5%, but it's actually 1.2%. So the p-value gives you a precise number for how uncertain, what chance it could be that you're rejecting the null hypothesis improperly is. Okay.
So basically, another way to say that is like there's a 1.2% chance that there is no difference between the population and the sample.
Yeah, I guess you could say that. That's not usually the way you would phrase it. Usually you would use this kind of the opposite, the converse way.
Right.
You'd use this as and remember how our hypothesis test is structured. Okay, our hypothesis is structured so that we have a null hypothesis. The mean is equal to this. The average number of slices that you get from a deli is 12. And so on and so forth. And what you're trying to do is to prove that that's wrong. Okay, so now, for instance, if I knew that the population of France, somebody did a study, surveyed every male between 40 and 60 in France, and their average blood pressure was 120, right? And then he came to the United States. I'm out of resources. I can't sample everybody in the United States. And he went out and randomly took a sample of 1,000 people from the United States. Now you could say, oh, let's see. My null hypothesis is that the average blood pressure for people in France is the same as for people in America. So mu for France is equal to mu for America. And since we know it's 120, mu for America is equal to 120. So now you can use your sample of 1,000 Americans to attempt to disprove that. In other words, you're going to wind up, if you take the average blood pressure of 1,000 Americans, you calculate your standard error, you find the difference between two populations. If the number of standard errors apart that they are is greater than 1.96, you say, well, I'm 95% certain that they're different. So I can say I reject the null hypothesis that the two populations are the same, and I accept the alternative that they're different, right? So now keep in mind, though, the way that this is structured is just because, let's say that you don't prove that. Let's say that the difference is 1.8 standard deviations apart, right? You fail to reject. You can't prove it with 95% certainty, less than 5% chance of being wrong. So you fail to reject. Do you say that they're equal now? No, you don't know if they're equal or not. You just you don't have enough evidence to reject the null hypothesis. So you don't say I accept the null hypothesis. You say I fail to reject the null hypothesis. So it's kind of backwards, right? We're really trying to disprove something. Anytime we're trying to use this kind of test, we're trying to disprove an equality, right? And if we fail, we haven't proved anything. We just failed to disprove it. Yes?
So it is always 95%?
No. You could have an alpha of 90%, 10%. In which case, think about this now. What would be your critical value for you got ahead of me. What would be your critical value for the z-score if you were willing to accept 10% chance of being wrong? What's a z-score where you got 5% here and 5% there? It's 90% confidence interval, 1.64. And if you want to be 90%, 99% certain, only 0.5% here and 0.5% here, right? Chance of being wrong, it would be 2. You would have to get standard error. You know, the 2.58 standard errors apart, right? You got that ahead of me, okay? And you can see because you want to be more confident, less chance of being wrong, you have to have a wider difference between the two of them in standard errors. Okay? I know that this is confusing the first time out because it's a whole new way of thinking about stuff. And they use this pretty rigorously. I mean, this idea, this construct of this hypothesis testing and the null hypothesis and alternative hypothesis, they really use this. You'll read studies and they're really talking about this stuff, right? So give it a little bit of time and some practice, and it'll become clearer as you